Okay, ternary terms. Okay, the whole thing up to now has basically been the purpose of what we're trying to do when we optimize things is to fit up the binary systems and get nice. When you're doing optimizations, you're trying first of all to do a critical evaluation and compilation of all the thermodynamic data for your binary systems to bring them all together and make everything self-consistent. Secondly, we're trying to get the binary parameters, which then permit us to estimate multi-component systems. So for that we've got to use the correct models, etc., etc. So the first terms here are the terms that you use if you fitted up the 3 binary systems and you want to estimate the ternary. And then, because it isn't going to fit perfectly, you've got to add ternary terms. Remember, the whole basis of the binary thing is that you're saying that all the information on bond energies and so on that you need for the ternary are obtained in the binaries. So the ternary interactions are weak compared to binary interactions, but of course they're not zero. So you have ternary terms. If you find that you then have experimental data for the ternary, you add a few ternary terms, which should be small, and then you can bring everything into sync with your ternary experimental data, and you get a nice fit to the ternary system. If you find that your ternary terms that you have to add are very large, or you need a large number of ternary terms which are very large and have strange composition dependencies, this is probably an indication that your model isn't very good. The model you're using, your physical model, chemical model to go from the binaries to the ternary isn't good. Now, you might even be able to put in 4 or 5 ternary terms and force fit the ternary. Fine, now you fitted the ternary, but then if you want to go to 4 and 5 component systems, it isn't going to work because you're showing yourself that your model isn't good. Right, so you always need ternary terms, but if you need a whole lot of big ternary terms, there's something wrong. First step might be to switch from between Kohler and Kohler tube a bit. Sometimes you find that can fix things up quite a bit. Or then you want to look back at your binaries and should we be using this model or should we be using short range order or whatever. But, did that just say I was supposed to update something? Now it's going to stop. Let's see what happens. Anyway, you do have to add ternary terms. So how do we add ternary terms? The ternary terms, of course, have to be 0 in the binary systems, and they should have some sort of a logical rationale. So if experimental ternary data are available, then these can be included to give empirical ternary terms. The terms must be 0 in all binary subsystems. These terms like this can be used. Q1, 2, 3, I, J, K, X1 to the I, just a simple polynomial term as a product of X1, X2, and X3 to the I, where all 3 are greater than or equal to 1. All 3 of the powers are equal to greater than or 1. These are then clearly 0 in every ternary system, as long as the powers here are positive in the ternary system, in the binary system 2, 3, X1 is 0, so this term is 0 in the ternaries. Okay, so if I, J, and this is a ternary term, if I, J, and K are all greater than or equal to 1, then these terms are 0 in every binary system, and that's a ternary term. And this is generally what people are using. However, such terms have little theoretical justification. It's not really. And it's also clear how the ternary term shouldn't be extrapolated into 4 or more components. Going back to what I just said before the break, if you've got a ternary, if your ternary systems are Kohler, tube, Muggiano, and so on, then we have this rationale, logical way to go to 4, 5, and 6 component systems. But if you have this in the ternary system, what do I do for the quaternary system here? I can't just write it like that. That isn't right. What do I do? So it's not quite clear. In fact, Sage, you're permitted to add these because you'll sometimes be taking data from other people or from stuff we did in the past and you don't want to re-optimize it, so you can add things like that. However, a more rational way is to really represent the effect of a third component upon the energy of a pair reaction. So you have alpha 1, 2 is a binary term, which you got from the 1, 2 system, so alpha 1, 2 reflects energies of 1, 2 pair interactions in the binary system. Now, how does adding 3 affect the energy of the 1, 2 interactions? And this then is the way we do it. A ternary term can be written this way. If this term isn't there, that's a binary term. This is the binary Kohler term back an hour ago along the Kohler line. if you have the system 1, 2, 3, and this is the polar line, this is alpha 1, 2, and the binary is here, and that is a line where x2 over x1 plus x2 equals constant. Okay, so this is your, if this x3, if this term here was a 1, then that's your binary term, and which the alpha, this first, all this here except for the last term is constant along this line. Then to give the effect of 3 on alpha 1, 2, you could add additional terms with x3, like this, x3 to the k. For k is 0, it's a binary term. For k is 1, that term is 0 in the binary system, and it means that x3 affects the alpha 1, 2. So this is an additional ternary term which you add, and we call this a, the way we generally do the notation is this as a 1, 2 brackets 3. In other words, it's giving the effective component 3 on the 1, 2 interactions. And the powers are I, j, k. The third powers, the I and j are these, and the k is this. So this is the notation we're using. This is a 1, 2 brackets 3 I, j, k term. Okay. If k is 0, a 1, 2, 3 I, j, 0 term is the same as a binary term. Okay, if k is greater than. So this ternary term is 0 in the 1, 2 binary, as it must be, and becomes bigger as you go along here. Or if you use a Redlich-Kister, then it's the same thing. That's the binary Redlich-Kister term, and you add on the term here. That's the notation we use. This would be this is exactly the same thing as this. It's just that if it's a Redlich-Kister, you use that. And that seems reasonable. If you're using a Kohler type thing and you want to go along like this, a line like this, well, then you're keeping the 1-2 ratio constant. It's the effect of 3. It seems to be the most logical way of doing it. So we generally, when you do a ternary term in FactSage with no other, if in FactSage you're adding a ternary term, I, j, k, and you don't make any other special specification, this is what you get. If the 1-2 system is treated by Kohler, then that's what your ternary term automatically looks like. Okay. If you now have a tube, so let's say we're doing it along here. So that's the line where x1 equals constant, and we're moving. So alpha 1, 2 is constant without any ternary terms. Alpha 1, 2 is constant along that line. So now I say, well, now you don't add x3, but it varies the ratio of x3 over x2 plus x3 as you move along. So this is what we're using here. As we move along, the first two terms here, this is what you would use. The first terms here are binary. Okay, so that's just what was in the previous section. Along this line, x1 is constant, so that's your binary term. And then your term with k is 0, you get the binary term. With k is 1, then it varies linearly as the ratio of 3 to 2 along that line. We could have put it x3 to the k, but I thought x0 over x2 plus x3 to the k was a little bit better. It varies as the ratio. So if this k is 1, it varies linearly along here. Otherwise, if you're getting up here, it can vary kind of. This seems to be a more well-behaved thing. So anyway, if you're using TOOP for 1, 2, and you don't make any other specification in FactSage, but you enter a ternary parameter, ij1 or ij2, that's what you get. And Redlich-Kister formula would be that. And if you use Muggiano, we do Muggiano this way actually with Muggiano. Okay, so Muggiano term is done the same way really as a Kohler term. Now here's the difference, and this is important. In any ternary system, 3 types of ternary terms may be included. Terms giving the effective component 3 upon alpha 1, 2, but you also have terms giving the effective component 1 on alpha 2, 3, and terms giving the effective component 2 on alpha 3, 1. A term like this is just sort of a strict. This kind of a thing is really nothing to do with the binary interactions. It's just a ternary empirical thing you add. This I think has a little more physical sense. I don't pretend it has a great deal of physical sense, but this ternary term gives you the effect of x3 on alpha 1, 2. Then you could also add ternary terms for the effect of 2 on alpha 1, 3, and you have ternary terms for the effect of 1 on alpha 2, 3. Okay. If you had Kohler 2, then you would be using For alpha 1, 2 and alpha 1, 3, you'd be using that type of thing down here, and for alpha 2, 3, you'd be using this type of term, and so you'd be having the effect of, and I think this gives a little more physical sense, especially if you're thinking, do I want to, you're doing the silica, calcium, magnesia system, we'd like to look at the effect of magnesia on the silica-calcium interactions. It isn't exactly that, I admit, things are getting more and more empirical as you go up, but still, there's some sort of so there's sort of three kinds of ternary terms here. Okay, and they're different mathematically. Now you can put this sort of thing into FactSage if you want as well. You specify that I want an old style ternary term, and it will let you do that as well. I wouldn't recommend you do any optimizations yourself using such terms, but if you're getting them from elsewhere, you want to do that. Similarly, this Muggiano stuff, we don't recommend. Nobody here uses Muggiano really ourselves, but you get Muggiano from other people who have done optimizations. You don't want to re-optimize it, so you can do Muggiano as well. And this kind of ternary term, if you want to read the paper and you like mathematics, the advantage to this kind of thing is that you can then go into this scheme of how you go from 3 to 4 to 5. If you use Kohler to Muggiano, can be made more sensible, logical, whereas this is pretty hard to justify how you're going to get such terms into multi-component systems, although we do have a way of doing it, because we had to. But this makes a little more sense. So you can read this, and then this is how you get, this tells you how you get, you can see it gets a little bit complicated mathematically, but hell, you got a computer to do all the mathematics, so there you go. So that's how FactSage works. Now, discussion, the present general permits several geometric models to combine in one multi-component database. For example, many ternary systems have already been evaluated with the Muggiano model. So we're doing a database for alloys. We have several alloys, A, B, C, D, which are all done using the Muggiano model. But then we add additional components, D, F, E, F, G, H, in which we're using Kohler 2. Now, we can, now that we have this scheme, we can put these things all together. Okay, otherwise before you say, well, if we're using one reason because you got to use Muggiano, other people have used Muggiano, so we can't add things to the database unless we continue on. Well, now you can. Okay, you can even mix them up in binary terms if you want, but I mean you can have several systems, like I say down here, you have several systems. For your 5 component systems, you have 3 or 4 systems that were done using Muggiano by somebody else. You want to just use their parameters and not have to re-optimize it. But the other systems, the new systems you're doing, you're using Kohler 2. Well, this lets you put the whole thing together. You specify in the database exactly what models were used to go into what ternary systems, and the whole thing can be put together this way. Similarly, if they use ternary terms of the x1 to the 1, x2 term, you can use those as well. Or you can use the terms like we're doing, or you can mix them up. So in one database for a 10-component system, you can have Kohler 2, Muggiano, R types of ternary terms, old types of ternary terms, it all can be made self-consistent. Okay, so that's what, so this made a big, once we had this, then this meant we could use all the stuff that other people had done and put it together with what we're doing without getting into trouble. They can't use our stuff because they don't have the programs for Kohler 2. But, well actually now they do have some Kohler 2, but they don't have the way of putting it together yet. So I don't know if this is good or bad. It means that our wonderful optimizations cannot be used by other people, but maybe that's good. Now, in terms of exactly how you specify this in the database, and how you indicate which one you want and the exceptions, and how you put things together in the groups 1, that's the sort of thing you ask your thesis advisor to do. I'm not going to show you how the database is set up, but we'll show you how the database is set up. Until we get a really good solution program in FactSage, the best way to set up the database, as I'm sure you've already found out, is to get a template. Get a template for a system that you already know, and you can see how the thing goes, or to ask a graduate student who's been trying to figure the thing out for the last 3 or 4 years, and he'll show you how to do it. Okay, but this is the theory behind it. This is what you're doing. And the final message is then the Kohler 2 Muggiano, the polynomial model and the Kohler 2 Muggiano using polynomials is based upon regular solution theory, extension of regular solution theory. It's not regular solution theory because you're extending things in terms of, you're not making your alpha functions constant. Also, you can have excess entropies, which are not 0, so you're taking into, in that you're taking into account the fact that you can have some deviation from ideal mixing and so on. But if you have large deviation from ideal mixing, then this isn't going to work, because that's what it's based upon. And it's no more complicated than the fact that you're assuming x1, x2 is the probability of a 1-2 bond. Alpha 1-2 is the energy of the 1-2 interactions in the binary systems, and you're saying that varies to the first approximation as x1, x2, which is the probability of finding a 1 particle next to a 2, which is only the case if the thing is more or less randomly mixed. If it's not randomly mixed, then that term doesn't have much sense. And this equation, then, you wouldn't expect this equation to work. All right, so you want to change the color scheme. Oh, I like that color scheme. Let's show this message again, damn right. Okay. Okay, so now at this point I should show you a whole lot of ternary systems which were calculated using the Kohler-Muggiano with 1 or 2 and a few small ternary terms, to show you that in many cases, however, you get really good results doing this. And this is not just disparage this whole method. And people that use the Muggiano and everywhere also get pretty good results. I mean, I'm not saying these things are no good at all, but, and so on. And I want to say, I mean, a lot of systems, you don't need any more sophisticated models than this, and everything works nicely, and you've seen hundreds of papers that are showing quite nice estimations of ternary systems using polynomials and so on. Okay. Now we're going to go beyond that, though, and we're going to go to systems where you really shouldn't be using polynomials because, well, for several reasons, but the main reason is simply that the systems are not randomly mixed. Even the assumption that 1, 2, 3, and 4 are randomly mixed on a lattice just doesn't work. Okay, so the first thing we're going to talk about is short-range ordering. Long-range ordering is basically two or more sublattices. So, I mean, something like sodium chloride is long-range ordered because the sodiums are on one lattice and the chlorines are on another lattice. Okay. We'll do that later. Short-range ordering, we're still talking about one lattice, and we're saying at a short distance of a few, 1, 2, 3, 4 atoms away from a central atom, it's ordered. So if I have a system AB, and I have a central atom A in a random solution, the probability of a B next to it is simply mole fraction of B. In a non-random solution, it may be much greater or less than that. If it has an A, it may have a tendency to surround itself with B's or to surround itself with other A's. That's short-range ordering in a nutshell. Okay, so let's see how short-range ordering affects, and we'll do short-range ordering, which is modified quasi-chemical model part 1, and then we'll be doing long-range ordering, which is more than one sublattice. Okay, so I have a, okay, before I, well, you don't have these things here, so you're just copying down when you go back and look at them. Kind of thought you might put these on your computers or something. All right, modeling, show this number 14. This is actually a talk we gave at CalFed a while ago. Okay. Okay, so we're going to talk about short-range ordering solutions. What I said then is you have a central atom. So short-range ordering can apply to solid solutions, apply to liquid solutions. You have a central atom, and it's actually more applicable even to ordering in liquid solutions is necessarily, and to a certain extent, short-range ordering. You can't have two sublattices in a liquid, although, as I'll show you later in the course, we sometimes make that as approximation because it simplifies life, but the principle in the liquid, of course, you have only short-range ordering. And a solid, you can have long-range ordering and short-range ordering. Talk about short-range ordering. We're talking about a single sublattice too. Okay, what happens when you get, so this is a PowerPoint number 14. All right, this is your aluminum calcium solutions. This is your heat of mixing. experimental heats of mixing in the aluminum calcium solutions. Now the dashed line there is what you get trying to Bragg-Williams model. This I've been using this, but the Bragg-Williams model is a random mixing model with a polynomial. What we've been doing so far is a Bragg-Williams model. Bragg-Williams is called a point model, or it means that you have all your lattice points and you have random mixing on the points, so it's a Bragg-Williams model. Now remember, the heat of mixing then in a Bragg-Williams model, the heat of mixing in a Bragg-Williams model would be x1, x2 times omega, where omega might be a power series, a plus bx plus cx squared or whatever, but you have the parabolic. It's always parabolic. Okay, now parabolic, but it's going to be modified. Okay, but because x1, x2, the reason it's parabolic is because it's Bragg-Williams, it's random mixed. x1, x2 is the probability of a 1-2 pair in a random mixture. That's where it comes from. Okay, and there's no way around it. You can put in a whole bunch of terms, but you still end up with something that looks quite parabolic, and you see it gets kind of rounded, especially at the ends. It's a parabola. It's a quadratic expression. You can try to flatten the thing out by putting in a whole lot of terms here, but you're forcing it. Now, look at the experiment. This is almost a straight line. All right, just take calcium and I add aluminum, you get almost a straight line. It's not a parabola. It has a little bit of curvature, but it's almost a straight line. Okay, now if the aluminum was going into the calcium, here you have calcium, this is liquid. You're going in, putting calcium, if every aluminum went in randomly, okay, then you get a heat of mixing because you'd be forming aluminum-calcium pairs, and the probability of an aluminum-calcium pair would be x1, x2, and you get a parabola. What's happening is it appears that every aluminum you add is giving it almost exactly the same energy effect as the previous aluminum. What that means is that every aluminum is surrounding itself by calcium. You're not getting any aluminum-aluminum pairs. If aluminum goes in, it surrounds itself by calcium. The next aluminum surrounds itself only with calcium, the next aluminum only with calcium, and so on. Okay, because the aluminum-calcium bonds are much stronger. Okay, it doesn't get next to another aluminum because those bonds aren't as strong. It stays away from the aluminum, tries to get as many calciums around it as possible. So every time you add an aluminum, you just increase the... and it's the same thing at this end. This is almost a straight line. Same thing, the calciums try to surround themselves by aluminum because the bonds are so much stronger. In the middle, it has to curve around a little bit. And it also, minimum is not at 50% anymore as it would be here, but the minimum is around 33%, which kind of indicates that you've got a maximum short-range ordering at the Al2Ca composition. Okay, which would mean that I would look at this liquid aluminum calcium. In the Lend region here, I would look at this as calcium on the lattice sites. Aluminum is going into the lattice sites, but surrounding itself with calcium. And this end, this is the other way around, but also the coordination numbers are now changing, so that you have a minimum at 33%, such that here you have aluminum surrounded by calciums mainly, calcium surrounded by aluminums mainly, but the ratio is 2 to 1. So it's like Al2Ca, sort of like a short range, it's sort of like a crystal structure. If you go from an aluminum, a short range, it's kind of like a crystal structure with an Al2Ca 2 to 1 ratio. Aluminum surrounded by calcium, calcium surrounded by aluminum, but the coordination numbers are double. Okay. So that's what this tells you. And you can see that you try to optimize. This was actually an optimization from somewhere, and this is not a parabola. This was fitted up to 4 or 5 coefficients. It's really not possible to fit something like this to a polynomial unless you have a whole lot of terms. Then you can generally force the thing into the middle, but at the edges, at the corners here, it just really is very hard to fit this up properly. And as I'll show later, even if you can fit it up properly, then you go to the ternary and it's all screwed up. Okay, so we got to have some way, a model. So the random mixing model is no good for this kind of a system. So what are we going to do? Okay, so this is your Bragg-Williams model. Okay, I'm going to present the short-range order, well, today and the next course in a somewhat non-rigorous way because I don't want to get bogged down in all the mathematics of the modified quasi-chemical model, which as you've seen, can be rather bogging. So I'm going to do the essence of it, the most important things of the short-range order, comparing the different ways of doing it. And then at the end, we'll go to the actual 2000 paper and show you the exact mathematics. But I don't want to get bogged down in the details. This is the major part, the essentials of the whole thing. So in the Bragg-Williams model, you have no short-range ordering. The configurational entropy is given by a random mixing. The heat of mixing is given by a polynomial expression, and the same thing for the SXS by a polynomial expression. And this was the enthalpy. So these aluminum scandium solutions, you see they're not quite as short-range ordered as the thick, using a Bragg-Williams model optimized by Litovsky and the people, and this is sort of was the best they could do, because it's too rounded. You kind of fit it in up here, but it's too. Now this is not as short-range ordered as the aluminum calcium. You can see the data are more rounded, but clearly you still can't get such a good fit. But let's look at some of the other things. This is also now, what happens if you have a, this is typical, that was your integral property, but what does the partial property look like? You can see this a little bit better with the partial property. Let's say you have a heat of mixing, and let's say the heat of mixing is this sharp minimum. Okay, the heat of mixing is the sharp minimum, one like okay, where it's more or less linear over here, goes quickly, and then there's more or less linear, like the aluminum calcium and so on. Okay, and we compare that to a heat of mixing which is parabolic. Okay, if the heat of mixing is parabolic, then delta H is omega XAXB, and delta HA is omega XB squared, as we said before. Okay, so if the integral is parabolic, Bragg-Williams, the partial is also parabolic, and this is XB squared, and you get a parabola. So this is the integral, the partial of D is a parabola like that. So that's your typical. So that dotted line, the dotted line is the Bragg-Williams, and that's your typical parabolic partial. Okay, now what happens, the partial of course is the intercept over here. Take a curve like this. You take a tangent here, and this point over here is the partial of B, and this point here is the partial of A. How does the partial of B work? So the partial of A. Partial of A is the intercept of the tangent line. Okay, if you're up here, this is almost a straight line, so delta HA is almost zero along here, very small, and then suddenly, very quickly, becomes negative and then becomes another constant. So delta HA tends to look like that, like a titration curve. This is the curve for delta HA. Delta HA remains almost zero up here, because that's the intercept here, then drops very quickly, and then it levels out to another value, which is the intercept down here. And so you get this typical curve that looks like this for a system which has ordering. And the place where it changes is the, now if it's very, very sharp ordering, this will go almost constant and drop almost vertically. And this shows some order, but this is definitely not parabolic. It's curving up like this, whereas you see this actually curves down this way. Okay, so this is, in this kind of shape is indicative of short-range ordering. Here I plotted delta H. I'll show you entropy later. GXS is delta H minus TSXS. So it tends to be dominated by delta H. So the GXS for GXS, or the partial GXS, RT log gamma, also tends to have this sort of. And well, I looked at it in the integral sense. I said that this is a straight line because every calcium you add to every aluminum you add to the calcium goes into the same spot, but that's the same thing with the partial. The partial heat of this component is constant here. Remember, the partial heat of mixing is the DH, DNA. The partial heat of mixing, of A is d delta H DNA. It's the rate of change of H as you add A. And if every A goes into exactly the same environment, then this is a constant. So you get a constant. Okay, so now what does the entropy look like then? This is what the entropy looks like. Remember, the entropy in an ideal, this is your ideal entropy up here. Your random mixing, x1 log x1 plus x2 log x2. In this aluminum scandium system here, or aluminum calcium even more so, you get a minimum, because this is your composition of ordering. Let's go back to the, what's going on there? Okay, as I said, this solution here at 33% tends to be aluminum surrounded by calcium surrounded by aluminum, so it has a very low entropy. It's quite ordered, it's highly ordered. Okay, so if it were completely ordered, the entropy of mixing would be 0. Okay, so what you're getting then is for the entropy, your entropy curve. In this system here, then the entropy of mixing, you expect it to look something like that. Well, this would be 33%. The more ordered, if it's ideal, mixing goes like that. This would be ordered. This would be even more ordered. The more ordered it is, the lower it goes. Okay, so this is an indication of. That's your other case of ordering. So if you have short range ordering, you tend to have the heat of mixing tends to be a negative V shape with 2 straight lines coming down. And the entropy of mixing tends to be a small M-shaped curve. Okay, and the further down this minimum is, the more ordered. Okay, so this is what you get. So how are we going to fit this up to a model? Okay, this is called the associate model. This is not the modified quasi-chemical model. This is the associate model. Just let me show you my notation. In the Bragg-Williams model, I used omega BW, omega Bragg-Williams, indicating that it's the omega for Bragg-Williams. Now I'm going to talk about omega associate is the omega, and as a parameter, that's your model parameter for the associate model. Okay, so now we're considering that the solution consists of A atoms, B atoms, and A, B associates. People use the word associate because they don't want to say molecule, but they mean molecule. So in this model, which is an ordering model, you will have one sublattice. Jesus, I hate these things, yeah. I don't know why they can't work. We have one sublattice, and on the sublattice we can have A atoms, we can have B atoms, or we can have AB associates. Right, we have molecules. It's not like I said A goes into, it's not what I said where you have calcium and then every aluminum goes into a surrounding of calcium. That's the modified quasi-chemical model, but this is another way of getting short-range ordering. Okay? And as you A and B tend to form AB associates, and there's a negative, omega AS, let's say, is negative, so that means you want to form these associates. Right? So this is a model that can be used for short-range ordering. And basically what we're saying is if this, you're forming an associate. So here, in this case, it's Al2Ca. So in this case, we would have A2B associates. Okay, so I start up here with pure B, and I start to add A, and as I add A, every time I add 2 A's, it forms an A2B molecule. Then I add 2 more A's, it forms another A2B molecule, and so you get a nice straight line, like that. Now, I don't believe this does not represent physical reality. In the aluminum calcium system, you don't have Al2Ca molecules. That's not what's happening. But if you did make this assumption, you would get quite a nice representation of the heat. Because it will still give you the straight lines. You're like forming a compound. Here you're mixing A and B, and the heat is just forming a compound. And the entropy of mixing also is going to go through the M shape. At 33%, you'll have Al2Ca, and it'll be okay. So this associate model can actually fit up binary systems quite nicely. So let's do the mathematics of the associate model. Okay, also the associates, now you form the associates, but once you form the associates, here I'm going to call them AB associates because that's how I did it. So this will give you a minimum at 50%. Once you form the associates, then the associates and the A and B are randomly distributed. So I've got the associates, but now A's, B's, and AB's are randomly distributed. It's sort of like a ternary system. You have A's, B's, and AB's distributed into 3 of them. The notation here in the AB, we're just looking now at the overall system. XA and XB are the overall mole fractions. That has nothing to do with the associates. It's just in the system AB, that's your mole fraction of A, that's your mole fraction of B. We'd have per mole of solution, we have XA moles of A total and XB moles of B total. But N prime A is the number of moles of unassociated A's, and NAB is the number of moles of associates. So we have 1 mole of solution, XA is the total overall number of moles of A, the A's and the A's and the AB's. So the total number of moles of A is the number of unassociated A's plus the number of AB's. And the number of moles of B overall is the number of unassociated B's plus NB. The configurational entropy then, as I said, is simply given by mixing the 3 types of, so this is a random mixture of N prime A unassociated A, N prime B unassociated B, and NAB B's, where the X primes now are the mole fractions of the species. XA is the overall thing, just as you define the system. XA prime is XA is the overall mole fraction of A in the entire system, including all the A's. XA prime is the fraction of unassociated A's. And the heat of mixing is then simply given by the fraction of associates times the energy of forming those associates. Omega S is the energy of that reaction, and so it's just delta H per mole is the number of moles of AB you have times omega AS. Okay, so this is your model. Now I skipped a few steps here because this was being given in a talk which was limited to 25 minutes. Okay, so now we can write delta G is equal to delta H minus T delta S. I could also I could make this omega a function of temperature, in which case I would have a non-configuration. I could put omega AS to be A plus BT, A minus BT, where B would be the non-configurational entropy of forming the AB if I wanted to. I'm not going to bother. Okay, XAB is this, so delta G is delta H minus T delta S would be XAB times omega AS plus RT. Okay. And now, what is the number, what is the number, the equilibrium number of associates is given by minimizing the Gibbs energy. Okay, so I take d delta G, dNAB, and I set it equal to 0, putting delta G into that expression, using these expressions and using the mass balance equations here. So a fixed composition of XA and XB, N prime A and N prime B are given in functions of NAB by this, and I differentiate the entire thing. And I'm going to let you do that for homework, for fun, but that's what I'm doing. I'm just taking this expression for delta H, this expression for delta H, using the mass balances, and this is a mass balance equation, and differentiating it. And what you end up with is you end up with an equilibrium constant for that reaction, as you might expect. This is simply the equilibrium constant for that reaction, delta. And this is all you're really doing when you're doing delta G's minus RT log K anyway. Okay, so the equilibrium constant for this is a chemical reaction. The equilibrium constant is the ratio of the mole fractions, because you're assuming it's an ideal solution in terms of the mixture, is exponent of minus omega over RT. Or omega is minus RT log K, if you like. And you can end up with this. Okay, so is omega, that's omega being negative. If omega is negative, then if omega is very negative, then this whole term is very positive. The equilibrium constant is large. Okay, so you tend to have as many ABs as possible. These reactions are shifted far to the right. Okay. And what that means then, if this shifted very far to the right, means that if I now have AB, and this is my heat of mixing, what it means is this is 50% here. Over on this side, I'll have B's and I'll have AB's, but I'll have very few A's because that reaction is shifted stronger. All the A's will react to form AB's. Essentially, they'll leave a few A's. So you get almost a straight line. And over on this side of the minimum, you have A's and you have AB's and you have very few B's. And at the midpoint here, you have almost exclusively AB. That's if omega is extremely negative. And your entropy then, your entropy curve is going to go to 0 here. Okay, so if omega AS is extremely negative, you get an entropy that has 2 humps going almost to 0, and it almost basically divides the system into 2 subsystems, a system AAB and a subsystem BAB. If omega is less negative, then of course you get some rounding and it rounds off. It becomes closer to a parabola, and this becomes closer to the ideal solution. And using the associate model, when you have negative values of omega associate, as you can fit up binary systems very nicely. So here is this is a system, hypothetical system AB at 1,000 Kelvin, 1,000 Celsius, calculated from the associate model with constant values of omega. So you can see if omega is slightly negative, you see, well, if omega is very negative, you have almost a straight line, flips around, comes almost a straight line here. As omega becomes less negative, it's halfway in between. It tends to be a straight line, but it gets more and more parabolic as you approach small values of omega. And this is what the excess entropy the actual entropy looks like. This is your ideal random mixing. I'll talk about this later, but this is actually not what you expect, but it's what you get. It's one of the reasons I don't like the associate model. Well, the main reason I don't like the associate model is it's not physically what happens, but anyway. But the heat entropy actually goes up, and then it comes back. So if omega is very negative, you get what you expect, and you play with it, and you get slightly negative, you actually get slightly positive excess entropy due to the fact that you have more particles now than your excess entropy's gone up because you're forming these AB particles. Like if you had an ideal mixing, you got A and B. Now you're forming AB particles, so you got more things to mix. Okay, so it kind of screws up a little bit, but it does tend to get down. So as long as omega is quite negative, you can get, it looks like this. You can get quite good fits. These, I think I showed here some of the fits, but basically, I didn't show it here. Anyway, you can fit up real systems quite nicely, binary systems using the associate model, even though it physically isn't too highly reasonable. I just had one more. It's 14A. This is a paper we did on magnesium aluminum tin. I just want to show you one more example. There's all sorts of examples. Magnesium, this is your magnesium tin system. Once again, you see that you get quite straight line down here, quite straight line along here, rounded in the middle. Okay. And what would happen actually, this is Mg2, it's based upon Mg2Sn. Okay, but the minimum is not at 30%. Not at 33%, it's somewhere between 33% and 5. We didn't here use the associate model, but it gives you the same thing. But if you, oh shit, the wrong one. I forgot what I was going to say. What was I going to say? Oh yeah, the something like this, the minute. Oh, okay, I'm going to show you. I'm going to go to the slide. Okay, here I chose the minimum to be 50% because I use AB associates, so fine. But if I chose the minimum to 33%, I would simply have A2B associates. And then if it was very strong, the minimum of this curve would be over 33%. But as it becomes weaker, and it becomes more just AB solution, the minimum will move back to 50%. So you find the shifting kind of. Because if you have very low tendency to association, it's going to be mainly a mixture of A and B, so the minimum is going to go back to 50%. So if you set the minimum at 33% by making A2B, you'll get the minimum at 33% for very negative omega, and then for very small omega, you get it back around 50%, and intermediate it would no problem. Anyway, you can get a pretty good fit for the. Okay, many systems are And you can look at all the papers we write and written with Ingo, and this is not just metals, we're talking about especially oxides and salts and so on. Short range ordering is actually the rule, not the exception. So short range ordering is, many systems have a lot of short range ordering. I showed this before, but it bears repeating. I'll keep going back here. All right, if you take this system, similar to what I said last week, but say, okay, well, in this region here, the Bragg-Williams and the short-range order don't give you that big a difference. And the partial property of aluminum, which is going to be very small, you take the tangent to here, okay, but you take something here and you take the tangent to this curve and the tangent to this curve, which gives you the partial heat of calcium. It can be very, very different, even though because of this curvature. And so your activity coefficient of calcium, depending on the fact that you've only got a small difference here, your activity coefficient of calcium can vary by orders of magnitude. And I showed a difference here. This was the, okay, this was your Bragg-Williams fit, and your, well, this was quasi-chemical, but you could have done this with these. So this is your taking into account short-range ordering and not. Okay, and now the other side goes this way, but you look here. Here we kind of fitted, they forced it to fit in, but on this side you see the associate, or the short-range ordering goes this way, the Bragg-Williams goes this way, and you end up with a really big difference in your partial property, even though the integral properties are pretty closely fitted over here. What is wrong with the associate model? Well, as I said, the associate model, there's some little problems like this business here, but the main thing is it's physically not reasonable. You don't have in aluminum calcium alloys, you don't have Al2Ca molecules. And that's going to really make a mess of things when you start to go to multi-component systems, which was the point of this presentation. I'll show you that next time. But let's just do it correctly with the quasi-chemical. Let's do it with the quasi-chemical model to show you the difference. The quasi-chemical model, we're going to model short-range order, but differently. We're not going to talk about molecules of AB. We're going to talk about probability of nearest neighbor pairs. All right? And we're going to model the short-range order in a different fashion, physically quite different. And so what we have is we have one sublattice. We do not have molecules. The A's and B's are put on the sublattices. Okay, the A's and B's go on the sublattices, but they are not arranged randomly. We arrange the pairs. That's an AA pair, that's a BB pair, that's an AB pair. Okay, we arrange the pairs on the pair sites. This is a, let's call it a pair site. This is a site for a pair, this is a site for a pair of atoms. Okay, so we're going to arrange the pairs of atoms, and we're going to say that the pairs are not randomly arranged. AB pairs, say, are more favorable than BB pairs. If it were random mixing, and I had an A here, the probability of a B here is XB. In a non-random mixing, the probability of the B here is greater or less than XB, and that's another way of looking at the short-range ordering. So in the associate model at 50%, we had AB. The associate model for something that's completely ordered was an AB molecule on every site. In the quasi-chemical model, the model for something at 50% that is completely ordered would be AB, 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 all B surrounded by A, all A surrounded by B. That's the way we're looking at the short-range order, as a preference for first nearest neighbors as opposed to the formation of molecules. Okay. So let's do the mathematics for the next couple of minutes for the quasi-chemical model. So this is what we're considering. We're considering an AA pair and a BB pair form two AB pairs in the solution. And for that pair exchange in the solution, we have omega. Quasi-chemical model is the parameter of the model. Now this is called a quasi-chemical reaction. That's why it's called it. It's not really, this is not a, in the associate model, that was actually a chemical reaction. A plus B forms an AB molecule. This is a pair, and this is a pair forming two other pairs. We call it a quasi-chemical model. Okay, Z is the coordination number. Z is the number of nearest neighbors around a central atom. Okay, so you have a mass balance. In 1 mole of solution, you have ZXA moles. You have XA moles of A, and it has Z nearest neighbors. Okay, those nearest neighbors are either NAA pairs or NAB pairs. So ZXA is twice the number of NAA pairs plus the number of AB pairs. The reason it's twice is because you're counting the AA pairs 2 times. And Z times the number of moles of B's is 2 times the number of moles of BB pairs plus the number of moles. This is just a mass. This is a quasi-chemical mass balance. The mass balance is very similar to the associate model mass balance, but it's a quasi-chemical mass balance. Okay, so that is the mass balance. Z is the coordination number, Nij is the moles of different kind of pairs. NAA is the number of moles of AA pairs in the solution, NBB is the number of moles of BB pairs. Xij are the pair fractions, it's the number of pairs Ij divided by the total number of pairs. If you want to prove, you got to have the number of 2 here. Let's calculate the total number of pairs. The number of pairs would be NAA plus NBB plus NAB. And from this is equal to 2ZXA plus XB. Sorry. Take the right-hand side of this equation, 2NAA plus NB plus 2NBB plus NB gives you 2NAA plus 2NBB plus 2NAAB, which is ZXA plus ZXB divided by 2. Okay, so the total number of pairs is where XAXB equals 1, which is Z over 2, which is correct, right? You have Z is the number of pairs around every central atom, so Z over 2 is the total number of pairs. So you have your quasi-chemical mass balance. I'm assuming for the moment that Z is independent of composition, but later on we can generalize. Total number of poles, this is the pair fractions. Okay, so now now we're still doing a random mixture, but we're doing a random mixture of the pairs over the pair sites. Okay, so we're not distributing atoms on atom sites anymore. We're saying these points here that I've written in the X are the pair sites, and we're distributing the pairs over the pair sites. Okay, and then we're distributing them randomly. So this is called whereas the Bragg-Williams model was called a point approximation, that is, you're distributing your atoms on points of the lattice. Now this is called a pair approximation, we're distributing the pairs randomly. Okay, so now if we're going to distribute the pairs randomly, and I found an error in this slide. There should be in this slide, so you can make this note, because otherwise you're not going to understand it. This should be minus R Z over 2. No, I missed the Z over 2. Oh, this equation is wrong. The configurational entropy is minus R Z over 2 times. And this is the number of pair sites. Z over 2 is the number of pair sites. We're talking about 1 mole. We're basing this on 1 mole of system A plus B. So in 1 mole of XA plus XB is 1. In 1 mole of solution, you have Z over 2 moles of pair sites. Okay, so you've got to multiply by the total number of pair sites. So that is the total number of pairs in 1 mole. When you have 1 mole of lattice sites, you have Z over 2 pairs. And now we're going to distribute the pairs, AA, BB, and AB pairs, randomly over the pair sites. So we have XAA log XAA plus XBB log XBB plus XAB log XAB. Okay, now it's a mixture, an ideal mixture of AAs, BBs, and AB pairs over Z over 2 moles of pair sites. Is that clear so far? The problem with this is that we cannot randomly distribute the pairs over the pair sites because, for example, if I have an AA, this is assuming that the pairs are randomly distributed. over the pair sites, but they bump into each other. If I put an AA pair here, I can't put a BB pair here because I've got an A at that lattice site. So putting an A, I don't have, it's not right, I can't, this overcounts the number of the distribution. Because now I'm limited. If I have an AA pair, this could be AB or this could be AA, but it can't be BB. So this gives you too big an entropy. Okay, so there's something wrong with this. Okay, so what we do is we fudge it. We say when. Okay, so this equation should hold for a system whether it's ordered or has no short range order. So let's suppose we have a system with no short range order. So this is the limit at which the system is just random mixture. If the short range order if this omega, we want when omega quasi-chemical goes to 0, we would like the system to become an ideal solution. Okay, so if we have no short range order, we should simply have an ideal solution. Okay, so now we fudge it in. When we have so we have no short range ordering, we should have an ideal solution. So when we have no short range ordering, the probability of an AA pair is equal to XA squared. So let's divide this by the value in an ideal solution. Putting XA squared here. Divide this by the value of an ideal solution, which is probability of the BB bond is XB squared. And the probability of an AB bond is 2XA XB. Because you can have AB or BA. Okay, so now in an ideal solution, in the limit where omega quasi-chemical model is 0, when you have an ideal solution, all these terms now go to 0. These terms are all 1, so the logs are all 0. And then we add on the ideal solution model minus our XA log XA plus XB log XB. Okay, so there is your quasi-chemical model, and it's an approximation. Now this then comes out correctly at the limit of ideal solution. So at the limit of an ideal solution, this whole first term becomes 0, and there's your ideal solution. Right, so this is how we mix them. We mix, it's a random mixture of AA, BB, and AB, and we fudge it in so that it comes in correctly for the ideal solution. The heat of mixing then is very similar now to what it was in the associate model. The heat of mixing now is the number of AB. There's a heat associated with this reaction. The omega could be A minus BT, so there could be a heat and a non-configurational entropy. But let's assume that there is no non-configurational entropy for the moment. So the heat of mixing then is the quasi-chemical parameter times the fraction of AB bonds. Every time you form an AB pair, you get a energy. This is also the same as you would get in a regular solution. I put it over 2 to make things come up. Okay, so, and then once again now, you do the same thing as we did in the same thing as I did in the associate model. You take G, delta G is delta H minus T delta S. You use this expression for delta H. You use this expression for delta S. You see it's very similar to what I did for the associate model. And you take d delta G, d number of AB bonds equal to 0, and solve it using the mass balances, and you end up with a equilibrium constant for the quasi-chemical reaction. Okay, so you get an equilibrium constant for this reaction, which is the number of AB pairs squared divided by the fraction of AB. The 4 comes out because it comes out, and this is, so you can compare this to the associate model, and you see it's very, very similar. In the associate model, this was the number of AB pairs, of AB molecules. Now it's the number, it's the fraction of AB nearest neighbor pairs. That's the same parameters here. The 4 is here mainly because I put the 2 down here. Don't worry about it. Okay, so then it's the same thing. If omega quasi-chemical model is very negative, XAB is going to vary more or less linearly on the two sides, and you're going to get the same thing. You're going to get heats of mixing which have a V shape. You're going to get an entropy of mixing which has an M shape. And since you can see the equations are so similar, you can get very, very similar fits with the associate model and with the quasi-chemical model, even though they're based on quite different ways of looking at the short range order. Okay. No, I'm not going to do this today because I don't have time. I'll do it next week. But this expression You can see this is an approximate expression. I put in the, I mix these things randomly, A's, B's on the pair sites, and then because that overcounts the distribution, because they bump into each other, I fudged in the answer. But it can be proven actually that this is exact in 2 dimensions. I'll show you that next week. But actually in 2 dimensions, if z equals 2, so in other words your lattice, sorry, 1 dimension, with z equals 2 is a 1-dimensional lattice. So your lattice is just like a long necklace, A, B, B, A, whatever. And a 1-dimensional lattice. If your lattice is just a lattice, one-dimensional, you can prove that that is an exact expression. It's not approximate, that is really the way you do it. And a 3-dimensional lattice, it's an approximate expression. And this certainly has consequences, which I'll discuss next week. This whole thing is called the Ising model. I'll talk about that next week too. Ising first developed it for 1 dimensions. So deriving this thing, actually showing this entropy, this, actually you can, to show that this is exact in 1 dimension, I'll show it next week, is pretty straightforward. So this is an exact equation for 1 dimension. That's quite straightforward to show. You can write, there is actually, we don't have to in principle make this approximation for a 3-dimensional lattice. For a 3-dimensional lattice, you can obtain an exact solution, in which the idea, it would seem very simple. You have a lattice A, as I showed, and you want to distribute the pairs randomly on the lattice sites, taking account of the fact that if this is an AA pair, that can't be a BB pair. That sounds like something that if you sat down for a couple of hours, you could work out, okay? Okay, Onsager worked it out in the 30s for a 2-dimensional lattice, and that was part of the reason he won the Nobel Prize. This goes on to pages and pages. No one has ever done it for a 3-dimensional lattice. It's an intractable statistical problem. It would seem so simple, just randomly distribute. You have a certain number of AA, BB, and AB pairs, and you just want to distribute them over a lattice site randomly, taking into account the fact that they can't bump into each other. It's extraordinarily difficult, apparently, in 3 dimensions. In 2 dimensions it can be done, but you would have expressions which went on forever. And I was told, I have no idea why, that it's relatively simple in 4 dimensions or more. I have no idea what that means. Okay, but anyway, it's called the Ising model. The 1-dimensional Ising model is the 1-dimensional Ising model. So what we're doing is, in the quasi-chemical model, we're really using the 1-dimensional Ising model and putting a Z in here. Okay, homework. So for next week, you might want to read this, the rest of this slide number 14, because I'll be going over that. And you want to read the modified quasi-chemical model part 1, which is number 17. Or 14 first, and then take a look at number 17, which is the modified quasi-chemical model for binary systems done with all the bells and whistles. Or you can just wait till next week, but at least look over number 14. For homework, try number 16. 17, number 16. Well, I guess 17, number 16. That's not 18, as I said, 17. This is the associate model. I said half an hour ago I took the associate model equation and I said you set d delta g, d number of associates equal to 0, and you can solve it to get the equilibrium constant. This is doing that. Just prove to yourself you know you can do it. You don't have to, or you don't have to. And then the other homework, this goes back to the Kohler Mugiano thing. These are from the old exams. You look at number 30 here, has all the various old exams. These are various things on Kohler Mugiano. So year 2003, control 2, questions 4 and 5. 2005, control number 1, number 6. 2005, control 2, number 3. and 2008, control 2, number 3. All these first three are in number 30 on the server, and the 2008 one is control 2, 2008 would be here, which I gave a number to actually. I called this 44 or 45. It should be number 46, I think. Anyway, you'll be able to you'll find that on the server.
Okay, thank you for your attention. Nope.